Hi grade 10, it's Gail here. I'll be talking you through 3 short videos on the trig functions and drawing their sketch graphs. We're starting off with the function y is equal to a sine bx. You've completed 3 trig investigations, and so you are aware of the manipulation of the sine function with the constants a and b. I'm not going to explain everything in detail again. We're going to start off with the specific case where y is equal to sine of x, which means that a is equal to 1 and b is equal to 1. When you are drawing the graph of any trig function, it's important to consider these 5 points that I've listed over here. The first is shape. You know from experience that the shape of the sine function is like that. It starts at the origin and it's the wave. You know the amplitude is 1, the period is 360 degrees, and the frequency of significant points. Now, in this case, significant points are turning points and where it crosses the x-axis, roots. So that is 90 degrees. And what happens at the origin? To check this, you can, on your calculator, just say sine of 0 degrees. And then you will get 0. And so you know at 0 degrees, the value of the function is 0. How are you going to use that to translate this information over here, this information to a sketch graph? Now remember, sketch graphs are not accurate. They are accurate in terms of shape and where the significant points are, but you don't have to be able to read off to the last degree what values are. So I know what the basic shape of this function is going to look like. I know the amplitude is 1, and I'm going to discuss that a bit further later. The period is 360 degrees, which means the pattern of the function repeats itself every 360 degrees. Significant points at 90, and at the origin, the value of the function is 0. And that is where I'm going to start. So I will plot my first point at the origin, which is there. The next significant point is at 90, and because I know the shape of this graph, I know it's going up or increasing. The next significant point is at 180, and it's on its way down. And then the next significant point is at 270, and the next significant point is at 360. Why have I drawn from 0 to 360? Well, because the period is 360 degrees, and so I've drawn an entire period. You draw the graph, and there you have it. You have the curve 1 period of the function y equal to sine x. Because it's a periodic function, it does continue with the same pattern in either direction. So it will go like that, and then over here it will be going up. The coordinates of the turning point usually need to be given, and so I'm going to fill them in here, and that is 270 degrees and -1. And here I have a sketch graph of y equal to sine x for the interval x is an element of 0 to 360. That means from 0 to 360 degrees. You need to know this graph very well. You need to be able to draw it in a couple of seconds at any time. I'm going to do a quick review of the concept of amplitude. The amplitude is defined as the maximum distance from the midline of that wave. So in this particular wave over here, the x-axis is the midline. It cuts the wave in half. It goes through the middle of the waves. So the maximum distance from this line to the graph at any point is 1. It's always at a turning point. So that's where we get the amplitude of 1. Even if this graph were shifted up, say to there, in this case, the midline would be the line y equal to 1, which is this dotted line here. And then the maximum distance from this midline to the curve, the most the distance could ever be, would be 1. That distance is also 1. This should clarify the concept of amplitude a bit. There's a separate PDF document that has got a summary of the basic graphs and the transformations with the constants a and b. Here's the note on y is equal to sine x, which is one of the graphs I said you need to learn very well. Here is the function y is equal to 3 over 2 sine x, which you're required to draw over the interval 0 to 360 degrees. So let's start with the 5-point plan. The first thing that you need to consider is the shape of this function, which you know is a sine function shape, like that. The second thing that you need to consider is the amplitude. And from your investigation into the function y is equal to a sine bx, you know that a changes the amplitude or affects the amplitude, and in fact a will be the amplitude, or the positive value of a will always be the amplitude, and a is positive in this case. So I can say my amplitude is 3 over 2. The third thing is the period. And because b is equal to 1, so it's just sine x, and we know what our sine x graph looks like, we know that the period is 360 degrees. Because we haven't tampered with the period at all, we know that there will be significant points every 90 degrees. And finally, what happens at the origin? And you can use your calculators for this. If you put a 0, you say 3 divided by 2 times sine of 0, you will get the answer 0. So that is going to be 0, 0. Let me just, origin. We will have the point 0 degrees and 0. Your first thing now is to set up the axes. You've got significant points happening every 90 degrees. So you'll mark 90-degree intervals along your axes up until 360 degrees. So that is 0, 90, 180, 270, and 360. On the y-axis, we need to go up to 1.5 and down to negative 1.5. So if I make that one, then immediately above it is 1.5. And if I make that negative 1, the block immediately below it is negative 1.5. I know that this graph starts at the origin, and I'm going to complete one wave over the 360 degrees with something happening every 90. Origin up to 1.5 this time. At 90, there we have a root, our next significant point, a turning point again, and there's our root. And then you draw the graph. You label your graph. You fill in the coordinates of your turning points, 270 degrees and negative 3 over 2. and 90 degrees and 3/2. And then you're finished. What would the graph look like if the function were y is equal to negative 3/2 sine x? You know from your Desmos investigation that the negative over here has the effect of reflecting the graph in the x-axis. The shape of the graph would look like this. It would go down first instead of going up first. The amplitude is unchanged. Amplitude is a distance, and so it's always positive. How we say that is the amplitude is always the absolute value of A. It's always the positive of whatever A is. The period is unchanged. You still, because the period's unchanged, you still have significant points every 90 degrees, and this graph still goes through the origin. I'm going to sketch that quickly. You start off at the origin. 90 degrees later, you are going down because you're reflecting it. So it goes to a turning point at negative 1.5, a root, a turning point, and a root. And then you draw that graph. So you can see that the blue graph is a reflection of the red graph in the x-axis. In this example, you have to draw a sketch graph of the function y is equal to sine 3x, and the interval this time will still be from 0 to 360 degrees. With the 5-point plan, the shape is a sine function. The amplitude is 1 because the value, this constant over here, A, is 1. The period has been changed. So in the general function y is equal to a sine bx, that is 1, so the amplitude is unchanged from y is equal to sine x, but we know that this affects the period. The 3 over here tells us that we will get 3 waves in 360 degrees. And so to find out, remember the period is how many degrees you take for one wave. So to find out what the period is, I'm going to take 360 and divide it by 3. And that will give me how many degrees I need for one wave. In the standard sine function that we did previously, we had a significant point every 90 degrees. We have shifted the period, and just like we did to find the new period, we divide by 3 here, which tells me there's a significant point every 30 degrees. The origin, you find out what happens at the origin using your calculator. So you would say, you would put into your calculator the sine of 3 times 0, and you would get 0. Setting up your axes, if that is 90 degrees, I know there's a significant point every 30 degrees. So it's 90, 180, 270, and 360. And I need my 30 degrees in between. The amplitude is 1, so the y-axis is fine. I'm going to start at the origin. And then the shape tells me I must go up. 30 degrees later, I'm going to have a turning point. 30 degrees later, a root. 30 degrees later, turning point negative. And so you go on. Onto the axis, then up to 1. Back onto the axis, down to -1, onto the axis, back up to 1, down to the axis, down to -1, and then back onto the axis. So this graph's going to be fun to draw. This is going to go up and down, up and down. Make sure you keep a curve and you don't make it look like zigzag straight lines. Sometimes the curves are not that great, but there we go. And remember, we said that we were going to get 3 waves in 360 degrees. There's the first wave, there's the second wave, and there's the third wave. The period is, however, 120 degrees. The last thing that you have to do is fill in the coordinates of the turning points. So there are lots of turning points, as long as you fill in the coordinates for an entire wave. So this would be the first one. So it's at 30 degrees and 1. And then here is the next turning point, which is at 90 degrees and -1. And then I'm back to the same point on the wave. I better fill that one in 2. So it's 120 degrees and 1. And now I've completed the turning points for a full wave. Label your function. Y is equal to the sine of 3x. Your axes are labeled, and so you're done. If you're drawing a sketch graph of the function y is equal to the sine of -x, you compare it to the standard form or the generalized form that we have over here. Y is equal to a sine bx. A is 1, so you know your amplitude is going to be 1. B is -1, which tells you that your period will still be 360 degrees, but you know from your investigation that with the sine function, the negative over here also had the effect of reflecting this function in the x-axis. So let's go on to the shape. The shape is going to be a reflected sine function. The amplitude is going to be 1. The period is 360 degrees. Significant points still every 90 degrees. And it'll go through the origin at 0, 0. So let's draw that. Here we go. Let's do our labels here. 90 degrees, 180 degrees, 270 degrees, 360 degrees. And then your turning points. 90 degrees and -1, and 270 degrees and 1, and you label your curve. Y is equal to the sine of -x. If you drew the graph of y is equal to the sine of -2x, and I'm not going to draw this one, we're just going to talk about it. The shape would still be a reflected curve. The amplitude would be 1. The period would be 180 degrees. So the period would change to 360 divided by 2. And you would get significant points at 90 degrees divided by 2, which is every 45 degrees. This is the last example I'm doing of the sine function. It's y is equal to -2 sine of a half x. By this stage, you should be starting to get used to this process. The general function y is equal to a sine bx. Just make a note for yourself when you look at this in the first instance that the graph will reflect in the x-axis, the amplitude will change to 2, and the period will also change, although people often make a mistake with this one, so we'll go through it in detail. Back to the 5-point plan, and I really do suggest that you are quite rigorous about this in grade 10. You can become more casual in grade 11 and 12. So the first thing you're considering is the shape. It's a sine function and it's a reflected sine function. The next thing is the amplitude. That's the distance from the x-axis, the maximum distance at the turning point, and it's the positive, the absolute value of A over here. So that is going to just simply be 2. Then the period is 360 degrees divided by a half. 360 degrees is the y equal to sine x period, and you're going to divide it by a half. So you all know this, but you forget to do it. You say 360 degrees divided by a half is 360 times by 2 over 1, which is 720 degrees. Just pause to think about this logically. This tells you that you're only going to get half the graph in 360 degrees. So it will take 720 degrees for the whole graph. The next thing is how frequently you get significant points. So the significant points are normally with the y equal to sine x function every 90 degrees. You're going to divide that by a half, which is the same as 90 degrees times by 2 over 1, which is every 180 degrees. And the last thing is what happens at the origin, and you should have got the message now that these sine functions are all going through the origin 0, 0. I'm going to plot that. I'm first going to set up my axes. So I'm going to go every 90 degrees just for clarity, but we know that significant points are only happening every 180 degrees. Let's just specify here that I'm drawing it from 0 to 360. The amplitude is 2, so I'm going to mark off 1, 2, and -1 and -2. And now I'm going to start plotting from the origin. The shape tells me it's inverted, so I'm going down, and the first significant point is 180 degrees later. So it's going to be at 180 minus 2, and then at 360 degrees and 0. In other words, I've just got this half of the graph over there, and we know that in 360 degrees we'll only get half of the graph. Draw that. Here's a turning point. It's at 180 degrees and -2. And you've got the graph of y is equal to -2 sine half x. And sometimes you don't get a whole one in. Sometimes you get 1.5 waves in. Things don't always fit into neat little boxes. Here is the whiteboard note that summarizes the general function y is equal to asinbx. And it just goes through the 5-point plan so that you can draw it every single time. The shape you've got to decide whether it is reflected in the x-axis. The amplitude is always the absolute value of A, the positive version of A. If A is negative, you reflect in the x-axis. The period is always 360, which is the period of the standard sine function, divided by the positive version of B, taken from there. If B is negative, you reflect it in the x-axis. You have significant points every 90 degrees, which is what it is with the standard sine function divided by the absolute value of B, and they go through the origin. I just want to point out that if you had the curve of the function y is equal to minus sine minus x, you would reflect in the x-axis for that negative, and then you would reflect again for that negative, and you would land up where you started. So 2 reflections in the x-axis and you back where you started.